Hi there, this is Alex Hussein from 3D Chimera, and today we're going to talk about design for additive manufacturing with SLS 3D printing. So we're going to cover some tips and tricks to help you guys be more successful with this technology. So on the screen here, you can see a couple examples of different SLS 3D printed parts that we've produced here on our Sintertech technology. So we'll talk a little bit about that as we go through the video today as well. In general, there are two different types of 3D printing that we do here at 3D Chimera. The most traditional type of 3D printing is called FDM or FFF 3D printing. In that technology, we start with a spool of plastic, kind of looks like a weed whacker line, and we push that through a hot extruder, almost like a hot glue gun. And we're basically pushing that through. It's melting the plastic down and it's extruding that out one layer at a time. That's typically how we see 3D printed parts out in the wild. Now we have a new technology here called SLS 3D printing, which is a powder-based 3D printer. So with powder-based 3D printing, we actually wipe powder across a build surface. We heat it up right before its melt temperature, and then we actually use a laser to selectively melt that powder in specific areas, building our object one layer at a time. It's really different than the other printing technology. So in the SLS technology, your part actually is completely encased in powder. So when the part is done, we actually kind of like brush it off and get all the powder out of it, kind of like an archaeological dig. Whereas in the FFF process, when we build an object, we usually are grabbing tools or something to break off support material or putting it in a tank to dissolve out the support. So as you might imagine, the SLS technology is going to give us a lot more freedom in terms of design and has a couple other cool things about it that we'll get into today as well. So that's really going to be our focus, SLS 3D printing. So some high level thoughts about SLS 3D printing. In general, when we print this technology, your parts are completely solid. So if you're familiar with FFF 3D printing, typically we have an infill pattern, kind of like a grid or something of that nature. We can control that density. In SLS, everything is completely solid. Whatever we feed into the software is precisely what we're going to get out as a solid block of material. What's really neat about that is when your parts are thicker, they're going to be very, very stiff and very, very strong. And interestingly, when they're thinner, they're going to be much more flexible, and you'll be able to bend them and twist them. Um, it's also a great technology because the two materials that we print with are highly chemically resistant. One is going to be PA12 nylon, and the other is actually TPE, which is a rubber type of material. So we have these two different capabilities. All the powders that we print are going to be like a dark gray color, and the parts can be dyed a black color if you wish, and there's some other post-processing techniques that can be done as well. So, a couple of the pros and cons here about the technology. On the positive side, we say complexity is free. So we'll get into that a little bit more today. But in general, that means that we can design in some very complicated geometries that I think people often think about with 3D printing, but they don't really have the ability to achieve in their everyday life with traditional FFF printing. So things like built-in interlocking features we can do, lattice structures. So that's like three-dimensional grid patterns, making things more lightweight we can do hollow parts we can print, crazy geometries that are, outside of what we normally see today. So things like topology optimized parts where we're actually using the computer to develop the geometry that's completely optimum for the part. So really minimizing material and forgetting about all the complexities of traditional manufacturing because with additive, we're able to do this and it really doesn't cost any more to have a very complicated part or very simple part. We talked a little bit about materials before. So PA12 nylon is a fantastic material, very strong, very stiff, commonly used in industry. And we also have a very unique material, a TPE, which is basically rubber. So we can actually print highly complicated rubber parts as well. So also very, very cool. Uh, the parts on off of this printer are going to be very, very detailed. We're talking about 100 micron layer resolution. So that's thinner than what we see on just about any other technologies out there. So you end up with really beautiful surface finish on your parts. In fact, a lot of our customers end up using these parts for completely end-use applications, either sold direct to consumer or as components inside of their machines or equipment. And most people who would interact with these parts would have no idea that they were 3D printed. It's a really fantastic process also for batch production. So in the FFF process, the traditional printing, um, you're building an object, and if you print one object, it takes let's say 5 hours. You print two objects, that's going to take 10 hours. You print three objects, that's going to take 15 hours, so on and so forth. So you really don't get any efficiency with that technology. Now, in the SLS process, we actually get huge efficiency as we start to add more parts. So what we're the main driver of time in this technology is actually the height of your parts in the Z direction. So the taller your parts are, the longer they take to print. But what's neat is whatever you can fill out in the grid pattern in the X and Y direction, that's going to print in roughly the same time as a single part. So let's say I have one part that takes 12 hours to print. If I can fit a dozen more of those parts inside of that same build volume, it could take still 12 hours to produce that whole dozen instead of, 12 times 12, right? So you've got some really great advantages there with this technology, and it works out amazingly well when you have lots of small parts. So if you got tiny parts, or they don't even have to be that small, things that are maybe an inch in size, 2 inches in size, we can nest them in 3D. They can kind of fill the entire three-dimensional build volume, complete that space, and we can print all those at the same time. And that's what we mean when we say batch processing. The parts also have a really nice surface finish on them. It's kind of a light textured surface. It's actually the surface of the powder, which is like 60 micron beads of powder. So very, very light texture on the parts. But what's neat is there's also lots of post processing that can be done. So we can definitely dye the parts, right? So black is a common color, but the parts can be painted. We can actually plate them with metal. We can do ceramic coatings on them, which can also be colored. And we can also polish the parts so they can get shiny, or we can add different textures to them just by doing some automated post processing. So there's really a lot that can be done with this technology that isn't even something you can think about with traditional FFF printing. Now, there are, of course, like anything, some shortcomings, some things to be aware of. One of the most important things is that in this technology, heat is super critical, right? We're controlling heat, and we're getting it exactly just below that melt temperature so that laser can melt it. What that means is as you are printing parts that have very thick walls or very solid geometries and that are very tall, you can start to see some minor warping in the parts. Now, all plastics warp a little bit due to shrinking because as plastic cools down, it shrinks just a little bit. Now, the more plastic there is there, the more warping that occurs. So the trick here with SLS 3D printing is to keep your walls thin. So imagining the type of rules you might follow for injection molding, those work really well here in SLS 3D printing. So that's one thing that's very important to think about. And the best way to avoid that is to just stick with smaller parts. So if you have a lot of small parts, that's really going to be the magic combo here for this technology. Um, Now, on the flip side, that batch process, which is such a huge advantage, can also be a bit of a disadvantage. So if you need just one part, one big part, it's not the most ideal process for that. Now, can we do it? Absolutely, not a problem. But you're not going to see that cost efficiency. You're not going to see that time efficiency there. So at that point, it starts to become more of a one-to-one comparison where you're looking purely at the geometry to see if the geometry could be printed in the FFF technology. That will definitely make more sense. Now, if your geometry is complex, it's still a great reason to use SLS, but that's something to think about. The other thing is material variety. So we do have these awesome materials, PA12 and TPE, but we don't have the huge plethora of materials out there that we do have in the FFF world. So if you have a very specific material need, then it might make sense to look at FFF. But if your applications just need strong plastic parts, PA12 nylon almost always is a good fit. And if your parts need flexible features, we can either use thin PA12 or we can actually use TPE, which is a thermoplastic elastomer, just like a rubber type of finish. So you can get a lot of good advantages there. Now, let's think about that size thing we talked about a little bit. So we have a pretty big build volume on our Sintertech technology. It's about 5 inches in diameter, about 14 inches tall. So if you guys are familiar with this like Yeti water bottle, we could absolutely print that entire thing inside of the Singer build volume without any problem. Now, would that be the most ideal application? We don't think so. And the main reason is we're talking about a really large part. We're really not getting any kind of efficiency out of that. So for a prototype, of course, it could work. But if you're looking at any kind of production application, that's not going to make a lot of sense because it's going to take a long time to just produce a single part. Now, on the flip side, the smaller components, right, the lid, perhaps this threading feature here that kind of creates the lip for it, those would be great fits for SLS 3D printing. They're smaller parts. We can nest them in. We could get dozens, maybe even hundreds of those parts inside of a single build volume. So in general, we say smaller parts are better. 3 by 3 by 3 inches is absolutely no problem. Um, Often even smaller parts. Imagine like the components that you might have in earbuds, the small bracket, the back of a remote control. Things at that type of scale tend to be an amazing fit for the technology where we can do literally hundreds of parts in a single batch and really get great efficiency. We actually did a project for the US Air Force not too long ago, and it was a small hydraulic bracket for the F-16 aircraft. And we were able to model those up from some old technical drawings, and we actually were able to print over 780 of those things in a single batch. Right now, the Air Force is grounding planes because they can't get these parts. And in literally 24 hours, we could print 780 of these parts, right? So 3D printing can really open up some amazing applications when it makes sense. And that's definitely one of those places. So a lot of small parts, you get a lot of advantage. Now, thin walls are great in SLS 3D printing. So parts that are designed for injection molding work really, really well, but we can't go too thin. So anything under about a half a millimeter in size is going to be challenging to print. On the other hand, anything 2 millimeters or bigger is going to be just super strong. So we've got a bit of a window there that we can work with. Um, but if you have parts that are thinner than that, that's going to be a challenge. Similarly, we could do lots of fine details. We recommend for nothing to be under about a millimeter in size. But as you can see here on this item on the right, we can do very, very fine details. So lots of details are great for this technology. As they get smaller, of course, they get weaker and more delicate, and that can be a bit of a challenge. But you can get a lot more detail out of this technology than you can out of just about anything else out there today. Now, when you're designing parts for SLS, it's very, very important that we think about how the parts are going to fit together. So, like anything, there are tolerances built into the machine itself, um, and we have to accommodate for those as we are designing. So, this chart on the bottom might look familiar to some of you guys if you visit our website. This is actually our most commonly visited page on our site. It has to do with the tolerances and gaps for 3D printing here. So you can see some dimensions here for designing with a press fit, a tight fit, a loose fit, a normal fit. So the normal type of engineering fits that you would be designing for. Now, it's very important also to think about just the general tolerances of your part. So, as your parts get bigger, you're going to see your tolerance grow. So that's really what we're looking at on the left-hand side. Kind of think about like half a millimeter or so, plus or minus a percentage of the length of your part. So the longer your part is, the greater that tolerance is going to be. The smaller your part is, obviously, the less critical that becomes. Another thing that's important, like any 3D printing, we are printing in layers. So it is possible for your parts to kind of get that topographical map type of an effect. So you just have to be aware of that and careful in your design. If there is a rounded surface that's important, certainly let us know. And in a print service, we can take care of that. And of course, in your designs, you want to think about the orientation of a part when it's printing. Now, orientation also matters when we're printing. So this is the same part here. You can look at it in two different orientations. Laying flat, it takes only about 2.5 hours. Standing up, it takes over 7 hours. Now, that's because in this process, the time is completely dependent on that height. So if you had like, let's say 3 or 4 parts, it might make sense to lay them out flat there. We could print all those in about 2.5 hours. Now, on the flip side, if you need to print a large quantity of those parts, let's say 20 or 30 of them, it might make a lot of sense to put it up on its side there and actually stack them in and print those over the course of 7 hours. So, there's a trade-off there. And it really makes sense to think about the volumes of parts you're looking at in order to think about the orientation for printing. So unlike in the FFF process, where we're really thinking about orientation primarily relating to the strength of the part, here we're much more focused on orientation in terms of getting the volume of parts through the machine as efficiently as possible. Now, going back to that idea of complexity is free, it's kind of a fun thought. What does that actually look like? So on the right-hand side here, you can see some axles and hinges in that design. That's an articulating joint. That's actually printed all as a single part. So the pins, the hinging features, the moving components, everything's printed at one time. We don't have any reason to split those things apart and assemble them together. We can actually design that from the very beginning to be printed as a single piece. Now, right next to that on the left-hand side is an example of what topology optimization looks like. So we can take a typical geometry, run that through any type of a CAD tool that has that feature. A good one is SolidWorks, but there's lots of others out there. And you're actually able to have the computer take all that computing power and put material where it needs to be and remove material where it doesn't. So you get really the most efficient part that you can possibly have. Then, of course, you can develop geometries that are otherwise impossible. So below that is a drone that's printed on the SLS technology. So you can see like those arms of the drone there. I'm not even sure how you'd produce that without 3D printing. Maybe like a lot of super glue and like rods or something. But it's a great technique for being able to make something that's lightweight, right, but still has lots of strength. And that can be modeled manually, or we can use that topology optimization. You've got a lot of different capabilities there that really before SLS 3D printing weren't even on the table. So it opens up a lot of interesting approaches to engineering. A couple other cool things here. Detailed text is possible. So we had a couple recommendations there in terms of size, but in general, we can emboss text, we can raise text, and it's actually going to show up. So if you've ever tried to do this in the FFF process, you'd know that it doesn't work so well. But here in SLS, we can get really good textures. In fact, you can see some of the letters here that are printed, and you can also see some different three-dimensional textures, which is another cool thing because in the real world, right, textures are applied to parts that are made of plastic, typically in the injection molding process, and almost always as like a chemical etching done to the tool. Where here, we can actually apply a three-dimensional texture inside of your 3D model and print that directly. This is really a total mind shift in the way that things are built. But SolidWorks, again, has an awesome 3D textures tool that allows you to put in all of those types of details. And you can see here the same exact design with three different textures. Those changes take maybe 1 or 2 minutes in CAD, and you can have a whole variety of different products. No need to worry about, like in the case of molding, huge investments in tooling. We can try lots of different things here or customize it for customers without any concern about it changing the cost when producing the parts. So, a couple big takeaways. In general, SLS works super well for short run production. So, batches of small parts, that's where you're going to get your strength. It's also great for fine details. So, if you have fine details in your parts that are maybe challenging in other technologies, this is a great one to think about. And SLS is going to allow for that complexity in your parts. So, you can push that design process to the next level. You don't have to worry as much about how your part is designed so that it can be produced. This technology is going to give you a lot of flexibility there. You can start to play with things like lattices and topology optimization that were just not even on the table before SLS 3D printing. So now what, right? I hope that was valuable for you guys. You got a lot of information. Sometimes when you're thinking about, how to take the next step forward, it can be helpful to have an experienced eye there to guide you through the process. That's exactly what we do here with our additive assessment. So if you're watching this video, we'd like to offer that to you for free. Reach out to our sales team here and we'll get you scheduled. Basically, what this will involve is some members of our team will do some video conferences with you. We'll ask you a series of questions, and we'll try to learn your goals for the year, both from an additive perspective, but also just from a business perspective to see where additive might make sense for your organization. And we'll provide back to you a short report that your team can review to see some of the opportunities where additive might make a difference on the bottom line. So with all that said, thank you very much for your time. Um, this is my contact information here. Feel free to shoot me an email anytime. That's my direct line. I'll be happy to chat with you. But I hope this was valuable for you. And if you have any questions, please don't hesitate to reach out.